Well, hello, everyone. Thank you for joining us. My name is Chris Buck. I'm the president and co-founder of Netlify, and standing next to me is Matt Billman, my co-founder and CEO, and he will be taking you through how we build a next-gen multi-cloud CDN to replace the web server. Now, a short intro of what we do for context, just quickly. Netlify is a developer platform that lets you build any web-facing property without actually having to run a web server. That means that you don't have to do server-side rendering. That's not needed. Now, we started just 3 years ago, and you might not know us yet, but we actually serve a bunch of the properties and tooling that you might know of, like Kubernetes and Docker and HashiCorp and serverless and JavaScript frameworks like React and Vue and React Native. A bunch of the most popular build tools out there in companies like Verizon, Citrix, Mozilla, and so on use us as well. Now today, there's already been a few talks, and it's interesting how we hear of so many takes basically on the same story, that many, if not most of you, are moving towards microservices and agile workflows to get more efficiency, more automation into your deployment workflows, reducing infrastructure costs, and so on. In many ways, it seems that you're all tasks every year of doing more with less. Now, these considerations of efficiency and simplicity that you all have for your infrastructure and your backend, now this is what we are here today to propose that you consider also extending to your web-facing properties as well. So without further ado, let's dive in.
Absolutely. So, as you see here, Netlify will build, deploy, and manage modern web projects. And when we talk about modern web projects, that comes from seeing a sort of architectural shift that's happened on the web the last 5 to 10 years or so gradually. These are some of the trends that we've been looking at in the marketplace, where Git has obviously become completely mainstream tooling that pretty much every front-end and back-end developer are using today. Microservices have had almost a meteoric rise, and at this conference there's a lot of talk about them. Modern JavaScript has gone from being a scripting language that you would use to sort of decorate HTML pages with a little bit of dynamic functionality, to being a modern runtime running inside essentially an operating system. And frameworks like React.js or Vue or Angular or Ember has taken front-end development and really brought like real software architecture to that space. And today people are building real applications in the browser. So if we look sort of the evolution of the web, before the web we had this very simple client-server model in the times of Unix, where you would take a client, log into a server, and maintain a session and send back and forth data. Then with the rise of the web, we started getting this architecture where you would have a client in the browser, talking to a web server that would talk to an app server, that would talk to a database, that would send back data, that would get mixed with templates, that would be turned into HTML and sent back to the web server and delivered to the client. And we had like that full cycle on every page refresh. And it was great. Like, it was what allowed us to build social web and Web 2.0 and e-commerce and all of that stuff. But now we're starting to see a shift as all of these tendencies from the previous slide are starting to come together, and we are getting browsers that are many, many times more powerful. They have gone from being just a document viewer to actually being an operating system. We're moving to a model where we have like a front end living directly on a content delivery network, talking to all kinds of different microservices. So we've sort of gone from a client service to a client services model. We talk about this in terms of a decoupled architecture, where people have started decoupling their web front end from all the microservices it talks to. And you get this kind of typical architecture with a build tool pushing to a content delivery network, a browser loading the front end and talking to different services. And front-end developers start adopting this kind of Git-centric workflow, where they work out of a Git repository. Every commit they make gets picked up by a continuous delivery engine, pushed directly to the edge, and runs there. And when we see this both for content-based sites where all the content is built out by a build tool instead of being built on the fly dynamically, or for applications where the front end is delivered directly to the client, we see obviously like a huge performance of the initial performance where the client will load the whole front end directly from a CDN without any moving parts. A ton of the malware that we traditionally dealt with goes away when we start removing the moving parts involved in serving a website. And we get this sort of infinite scalability of a content delivery network that's distributed all over the world instead of relying on a single point of origin that tends to fail a lot more often. We've like a bunch of people have started to talk about this architecture as the jam stack, sort of saying that the architecture that the stack has moved up a little, where it used to be things like the LAMP stack, where we're talking about the Linux, Apache, MySQL, PHP, like the specific server software, the specific programming language, the database we're using, and the operating system we're using, to talking about JavaScript as the runtime in the browser, markup as the delivery mechanism, and APIs as the dynamic services we talk through. And if we look at this way of developing for the web, there's sort of a parallel to how mobile app development came to be. When mobile apps got introduced and there was sort of a chance of inventing a new stack, no one thought, let's make it so every time people do an interaction on their phone, the phone will download a new version of the UI from the server and present it to the user. It was sort of very natural to instead think you have some distribution mechanism, the phone gets an app installed and then talks from that app to lots of microservices. The typical mobile app will talk to Twilio and an authentication service and file storage services, all from the app. The delivery mechanism is typically some cumbersome gated store owned by a proprietary publisher. But the architecture is very sound. And what we're starting to see is the front end starting to adopt the same kind of architecture, where we have some kind of CI/CD as a delivery mechanism. We have a front end, a static front end living directly on a content delivery network, and then talking to all these different microservices. And one of the things that starts happening when we start moving towards that kind of architecture is that we need some orchestration layers to keep track of all these microservices and to essentially do what service discovery has done for backend infrastructures for the front end. And that becomes a logical point to combine the CDN layer with a gateway layer that acts as a sort of intermediary between the front end and all these different services. And one of the things we see at the service side of things is that we've seen the rise recently of serverless functions. And one of the things that's really promising for front-end developers for serverless functions is that once you start having these small decoupled microservices on the back end, either running other people's services like Stripe or MailChimp or Pusher or anything like that, or your own internal microservices running in Kubernetes clusters, maybe on top of an OpenStack infrastructure. As a front-end developer, if you have some place where you can write a little glue code, you can build very complex and advanced projects without the support from any of these backend developers. Just try writing a little bit of glue code to tie together different services. Think about a subscription service built with a product like Stripe. The only thing you really need in server-side code is like 5 lines of code that has the Stripe secret token and can create a subscription and update a user service. But if you suddenly have to have a whole backend just to build that little part, then a lot of this architecture gets lost in a way, right? Like then suddenly you have to worry about running additional servers to tie these things together. The promise of systems like AWS Lambda and similar serverless functions is that front-end developers can simply write a little glue code and tie all of this together. And then as you start having this gateway layer, you start getting a really solid architecture where front-end developers can take projects much further than they could before. So Netlify came about because we saw this shift in architecture happening, and we started seeing what was possible by decoupling the front end and the back end and adopting this kind of infrastructure. But we also saw that for a lot of people, it meant suddenly having to stitch together a very large set of different services that were not necessarily aware of each other. To work efficiently with this kind of infrastructure, you also need a very large layer of automation. You want to make sure every time there's a commit to Git, it gets picked up and it gets deployed. And you start needing this kind of gateway layer to route to your serverless functions and your microservices. And if all of these things lives in completely different places and are unaware of each other, it can tend to be really, really cumbersome to maintain and to get any overview and to build. So before we dive further into the whole multi-cloud part and so on, I want to just do a quick live demo of how Netlify actually works. And I'll have to do this while looking at a monitor down there, so we'll see if I can hit the right buttons. How many of you know this, the GitHub repository called Create React App? There's only a few. So Create React App is a boilerplate around React, which is, of course, like the most popular front-end framework right now. It's built by the team behind React to make it easier to get started with new React applications. We maintain a little fork of this that's called Create React App Lambda. And this is meant for starting new projects that has a React front-end, a layer of AWS Lambda, and then talk to different services. And as part of our fork, we have a little deploy to Netlify button that I'll click now. So when I click through this button, I can connect to GitHub and can tailor this to OpenStack. Now, what Netlify is doing now is taking this boilerplate of a new React application. It's giving me a new repository in my GitHub account. And it's configured a fully production-ready continuous deployment setup, deploying to a multi-cloud CDN spanning across 7 different global cloud providers. You'll see the initial build running now inside our Kubernetes cluster, installing all the initial dependencies. Our system will automatically detect all the common dependency formats and then cache dependencies between builds. So in this first build, you'll see the usual waiting time for installing all of the internet through NPM. And then after this deploy, every other deploy will skip that step completely. Now we have the front-end build tool running, pushing out a React static front-end and a Lambda function. And now the new site is live. And let me just go here and visit the site on a new URL. So this is a new front end delivered directly from a CDN. And one change from the standard Create React Lab, it doesn't have the little button called Call a Lambda that we've introduced here. And if I go in and click this one, that'll talk directly to the CDN. It'll send a little request to a relative path on the same URL I'm at. .netlify/function/hello. That from there, our CDN will directly invoke the Lambda function we deployed and give us back this little hello world message that shows up. And if we go to the new GitHub repository that we set up in the process, this is, as I mentioned, it's just the normal boilerplate from Create React App, but with a new folder called Lambda. And in here, there's like a single file called hello.js. Our automation layer makes this simple to write these serverless functions. You simply just include them in a folder together with your front end. And then we'll set up all the routing, do all the deploys. Let's make a little pull request with a change to this function. Immediately now when I make this pull request, you'll see that Netlify picks up that there's a new pull request and start running a new build. And if we go in here, we'll go in and we'll start seeing the build logs from this. This time there won't be any dependencies to cache to install since they're already cached, and you can see the build already started now. Building a new version of the front end and of this Lambda, there won't be any changes, so Netlify is smart enough to not deploy a new version of the front end and just deploy the single Lambda function that we built. And now we have this little URL called the deploy preview. You'll see it starts with deploy preview 1 and then the same URL we had before. And when I call the Lambda function from here, I get hello OpenStack. if I go back to the production URL and call it, I get hello world. So we've essentially just with this one-click setup got a workflow for our front end where every single pull request becomes an independent staging environment, and where every single Lambda is an immutable functions, where from this list I can do rollbacks instantly, I can preview any old version of the site, I can go into the settings part, set up environment variables for things that the function should be aware of, but that shouldn't live in the front end code.
So yeah, just to extend a little bit on that. So when your front end teams generally work, they have all their workflows centered around gets. Yeah. So when they need to set up automation and when they need to run serverless functions or anything like that, that's when they reach out to your DevOps team. But this integrates it. So functions, instead of having to front end developers set up Lambda or something like it, what they're really doing is just have a website folder, put the code in there, and that's it. Or put the code in a repo. And the automation is out of the box as well. So it's really just tying the front end together with the workflows of anyone that's working on your backend much tighter.
Precisely. So to dive into what you just saw here, obviously part of Netlify is this Multicloud CDN that we deploy to, that's really built to being the origin distributed all over the world. Instead of having a single point of origin behind it, you do deploys directly to this. We build it to enforce the idea of atomic deploys. So when you have this kind of front-end application, if you just use like an object store like S3 or Swift or anything like that, and you just naively upload new files whenever there's a deploy, you'll often have this consistency issue where there's no concept in that object store of an actual deploy entity. So if you have a large content-driven site, for example, and you change the sidebar and you start uploading, every time that happens, your site will be in some inconsistent state where a new category page might be added and all the new pages linked to it, but it hasn't been uploaded yet. So we've built this to make sure that we can give these kind of guarantees that every deploy has an atomic state, and as soon as the files are ready, if a switch is flipped and the new version is live on the CDN with instant cache and validation and a very high level of cacheability on the edge nodes, also for the actual HTML pages. We've built this to be truly multi-cloud, so I'll dive into that a little deeper. But currently we run points of presence across AWS, Google Compute, DigitalOcean, Rackspace, Azure, Host Virtual, and Alibaba. And running, like owning the software that runs on the edge, allow us to also take some of the declarative edge logic that you used to need an Origin web server for and just push it directly to the edge nodes. The Lambda invocation is one example, but there's many more. Part of this is obviously also the whole CI/CD workflow I just demonstrated, which has this very deep integration between the CDN layer and Git. So every pull request will give its own URL. Every time you open up a new branch, you can deploy that branch and get a unique URL for it. So if you just create a branch called staging, then you have your staging environment as a long-lived URL on staging.whatever-domain-you-want.com. And it's completely no ops, right, from one end to the other. And then on top of that, we have this layer, this gateway layer I talked about, where of course we both have this kind of like Lambda integration. We have an identity service, seeing that one of the pieces to make this kind of architecture work, where you have all these different microservices that should be really decoupled and not aware of each other, is the idea of stateless authentication, where instead of all these microservices having some central service they need to be aware of and talk to know if a user is authenticated or not, you pass around a cryptographically signed JSON Web Token, and each service can just verify the signature of that token to know the state of the current user. And then the gateway layer, of course, can set up routes to proxy directly from the CDN to all the different microservices and apply logic at the edge around authentication rules or location-based rules or any of those. So to dig a little further into the actual multi-cloud CDN we built. So we are at Netlify, we are obviously very strong believers in infrastructure as code. So there's like an initial layer orchestrating all of this, built around a GitHub repository where all the state and all the nodes and all the points of presence of our CDN lives in. That repository will, on the one hand, have the Terraform recipes and the Terraform state that control all the instances across all these different cloud providers. So Terraform is an open source tool by HashiCorp that you hopefully all know about, that allows you to just define the state of the infrastructure you want in terms of like what instances do I want live in what regions, based on what images, with what network rules, with what security rules. So that's probably one of the keys to allowing us to easily manage servers across all of these cloud providers and with more coming. The next part is, in our case, is Ansible, where all the recipes can live in the same repository and where the canonical host file lives describing all of the current CDN POPs. And obviously Ansible we run to configure every new CDN node and also allow us to run tasks across all of them. We use a DNS-based traffic director where we've partnered with NS1. NS1 is we did a lot of research before partnering and are consistently placed in the top 3 fastest performing DNS providers in the space globally, and allow us to do very, very high quality traffic direction based on either geolocation of the user or with the Pulse product based on the actual latency to the individual CDN POPs from the user's ISP and location. Then we have our own layer of software running across all of these cloud providers. We've built our CDN on a proxy cache called Apache Traffic Server. That's not the most well known. More people will probably know about products like Varnish. Apache Traffic Server came out of Inktomi way back in the day, got bought by Yahoo, got forgotten for several years, and someone found it in the dusty cellars of Yahoo and discovered that it was a really, really powerful proxy cache, and then they open sourced it and gave it to the Apache Foundation. And today it's a very active project. It's powering Apple's CDN, eBay's CDN, LinkedIn's CDN, and all of Yahoo, and our CDN as well. We have our own proprietary plugins for Apache Traffic Server that implements the whole concept around atomic deploys, about the lazy SSL provisioning, so we can do one-click rollouts of new certificates across the CDN and so on. And then right behind these nodes, there's a bit of our own software sitting in terms of a little proxy and DNS manager. The proxy is the one that acts as the microservice gateway. It's a high-performing proxy, being able to invoke all of these rules to distribute the traffic. The DNS manager runs to keep NS1 up to date with all the POPs. It also constantly runs health checks across all of our points of presence, and will report those back into NS1. So we can instantly route around any problem with any specific cloud provider in any specific region. So if someone rolls out a back configuration file on AWS and takes down all of their infrastructure, our infrastructure will just register that through health checks running across all the different cloud providers and just start routing traffic around it. The same happens if someone takes down. We've seen that happen in some of our POPs on DigitalOcean or Rackspace with denial of service attacks, where they have far less. We've seen that they have less mitigation capabilities than the really big players. We'll just automatically detect that and start routing around those nodes. Then, of course, we also have an origin layer that runs the whole deployment mechanism, that runs the API that every single deploy goes through, and that serves as the canonical file store for every single object uploaded to Netlify. One of the things that allow us to build this kind of immutable deploy system for both the Lambda functions and the actual front-end deploys, and allows us to do the very fast pull request-based versions and the rollbacks and branch-based routing, is that we've built our own Merkle tree-based storage engine across some of the large object store implementations. So you can find a post on Medium by our CTO describing more in detail how that's built, but it's basically the idea of taking the same architecture that Git uses to be able to allow branches and version controls, and building that kind of file system on top of all the major open storage providers, object storage providers. So in AWS, we use S3, in Google Compute, we use Google Storage, and in Rackspace, we use their cloud storage product built on top of OpenStack. And then we have a little blob sync program running that constantly replicates any uploaded file across the different storage mechanisms and keep track of where each file persisted. We have a MongoDB-based layer using a little special since we use RocksDB as a storage engine, but using MongoDB as the whole query interface that keeps track of all the metadata of every single deploy, which tree does it point at, and so on. That runs as a replica set. And we have individual replica sets we have one replica set spanning all these different cloud providers. One of the powerful things that MongoDB gives us in this case is that it can have a concept of a set of nodes that are hidden. So in case of an accident, it will give priority to nodes in the same data center, and then only if all of those nodes are unavailable will it do a full master failover to one of the other cloud providers. So that allows us to keep a replica set running across these three cloud providers without risking cases where we'll accidentally just suddenly send our master to a different cloud provider than our app service is running in. But at the same time, all of this gives us the flexibility of doing a failover where each of our app servers running in each of these cloud providers, there'll always be like an active cloud provider for this origin layer. We'll have a preference set, so it will, if you talk to an app server within AWS, it will always try to find any file objects in S3. If you talk to an app server in Google Compute, it will try to find any file object in Google Cloud Storage. But if that object, if it can't connect to Google's cloud storage because they have a networking issue, or if the object hasn't been synced properly, or it's just not there, it will have a list of priorities of which ones have the best latencies from there, and then try to fetch the object from either S3 or from OpenStack's file storage. And in the same way, it of course, MongoDB's master failover process works quite well with these app servers. So if there is suddenly a failover from our MongoDB cluster to another provider, all the app servers will simply start talking to the right master. And then we have this CDN layer, which we own ourselves, and there we use Console, which is HashiCorp's service discovery product, running across all these CDN nodes and being aware of some of the state, like which one is the active cloud provider right now. And that means that we have the ability to simply flip a setting in Console and start sending the traffic from the CDN from the primary cloud provider to a secondary cloud provider. We went from a journey where we started all of this in a single cloud provider, in this case Rackspace, and then started gradually building out these capabilities of replication and so on. And about 2 months ago, we did the first test failover from one cloud provider to the other a Sunday afternoon when we could see the traffic patterns were at their lowest. And we're able to execute a complete failover with all the database, all the application server, all the API traffic, all the object storage within seconds without any user-facing problems. Like not a single user experienced an issue because of that. So that's powerful. It's painful and takes a long time to build and run. But once you have it, it's an incredibly powerful property to be able to just say, okay, S3 is experiencing issues. Let's swap away from AWS today. Google Compute is having an internal networking issue, which they've had a couple of let's switch traffic over. So how do we know when we have a main provider that these secondary providers are really ready to take over traffic? One of the things we've done there is that while the CDN is aware of the primary provider and send all of the traffic there, it will sample a small number of requests and send them to the secondary providers for verification, so we can see that those secondary providers can serve traffic correctly. And that way we can keep an internal health monitor on the system and know the state of the health states also of the providers that are not currently serving traffic. So that's a bit of our journey to build this large multi-cloud system for the front end. It's very important for us that while we run a ton of infrastructure and while the term serverless can sometimes sound a little funny to us when we are maintaining servers across all these different providers and are very aware of their existence, the benefits of this kind of tooling is all in the workflow for the front-end developers. It's all about having built all of this in a very special purpose way and a very tightly integrated way, so we can essentially take all the operations away from front-end teams. One of the things I think that most people have probably seen is the complexity of front-end development growing incredibly in the last 5 years. 5 years ago, our experience with front-end developers was very much that you had like someone that would take a PSD and then slice it into HTML and CSS and hand it over to a backend developer for implementation. Today, front-end developers are using advanced JavaScript frameworks, and they're compiling stuff. They're using continuous deployment, and they're working in a browser environment that has grown to be a fully fledged operating system where your APIs are not like desktop operating system APIs, but web APIs and microservices and serverless functions. And this means that if we want front-end teams to keep functioning and be able to push the boundaries, we have to take away some other complexity in order to give them space to work. So that's the purpose in building up this kind of automated and very integrated CDN, continuous delivery, and API gateway, and serverless distribution functionality, to be able to say to front-end teams, now you can set up a new continuous deployment workflow for a project in 30 seconds. You have a place where all the complexities of managing your serverless functions and figuring out how to connect to the different microservices are handled, and you know out of the box that all the performance characteristics of your front end are taken care of. And then, of course, for larger companies, it also gives the advantage of having the front end live on one platform where they can get an overview of all sites deployed, of all deploys happened, of workflows around who can actually deploy the master branch, and overview, auditing, SLAs, and so on and so on. The other big benefit, of course, is that when we can remove this concept of an origin or a traditional web server and distribute the actual HTML files in the front-end application directly to a content delivery network, we get so much better time to first byte, which translate to much faster load times, which in terms translate to much higher conversion rate. That's sort of very well understood knowledge by now. We also get global performance. So a lot of people, I've seen that happen a lot with front-end developers that are more in a mindset of just thinking of their code, and they'll run performance tests on the front-end code, which is super important, plays a huge role in performance. But then they'll run it always from some location that's close to where their origin server lives. And then when someone visits the site from Tokyo, they'll discover that from Tokyo there's a more than 1 second time to first byte for every visit, and all their optimization work is basically in vain, right? Because that's already pushing beyond what gives a good experience. And then, of course, there's a huge performance and a huge benefit in this kind of multi-cloud infrastructure where we can route around all the specific issues of specific providers. We get a huge resilience because whenever we've experienced anything that's not a layer 7 DDoS attack, but anything lower in the stack against these different cloud providers, it's very different how each of them are geared to respond to specifically that attack. In this way, we always get the best of breed, since we'll simply transition out any cloud provider that can't really handle it. And then, of course, from an architectural perspective, there's huge security benefits. As soon as we decouple runtime from hosting, from content-driven side built out with static site generators, it's sort of a no-brainer that you go from a world where WordPress and Drupal and all of those are breeding grounds for malware. At our network, we get around 60 million requests a month, starting with WP admin, even if you can't host a WordPress site on Netlify, just from automated malware looking from unupdated WordPress installs or plugins that they can infect. As soon as you decouple that layer from the build layer, you take away all of those security exploits. And then just by moving from these very large monolithic frameworks to a decoupled architecture where each microservice is decoupled and much easier to understand, it's also much easier to secure the surface area of those individual microservices. And as we see these microservices get smaller, they also start getting more reusable, which means we start seeing more third-party providers like Stripe for payments, or Algolia for search, or Contentful for content management, and so on, that will manage that specific service and have their own security on it, and so on. And then, of course, having this idea of immutable deploys also means that one of the big sources of something going wrong, whether it's reliability or security, is often having made a change that wasn't what it should have been. So having this capacity to instantly roll back your front end to a known good place is really powerful.
Yeah, so I guess we're talking about a web that is increasingly moving towards microservices. We're here to try to close the loop, so to speak, and part of that solution is a Multicloud CDN that's the first to be made to be the origin. It's architected to be the origin rather than a typical CDN, which is always meant in one way or another to be in front of an origin, to be a caching layer. So if you guys are curious in any way about how you can better tie the front end in the organizations towards the rest of the show, so to speak, like the way you work with backend and infrastructure and all the workflows and the efficiencies there, we'd love to talk more to you about that. And also, if you or someone in your org currently, does anyone here know what your organizations are running as far as web-facing properties? Anyone here on WordPress? Drupal? Static sites? No? Okay. But if you guys are looking to, more, for example, move off Drupal or WordPress or anything like it, then Netlify also runs the most popular open source headless CMS on the market right now. So it's actually just completely Git-based, and then it's completely open source as well. So it'll work on any solution there. And we'd love to chat to you guys more about this. Obviously, we're here because we bring service discovery for the front end at a conference that's mostly about service discovery for the back end. We're here the rest of today and tomorrow, and we'd love to hear more about how you are working with web-facing properties in your organizations, and if any of these challenges around workflows and silos and so on is something that's familiar to you. We'd love to chat more about that. But anyway, thank you so much for your attention today, and thanks for letting us. So. Thank you.